Well, thank you everyone for being here. This is Francis month, and this is Francis session for the month of July. We're going to talk about geothermal energy in France and other interesting topics related to that. So we have here today our collaborators and presentators, Pierre Dost, Christophe Kerbeban, and Cristel Desayos. Okay, so thank you for being here today and helping us to organize this meeting. And we're going to start with Pierre's presentation about a geothermal exploitation in France, its status, permitting, and data sharing. Now, I'm going to give you a little bit of information about Pierre. Since 2022, Pierre Dost has worked at PRGM on CO2 storage, water resource management, and geothermal energy. He has been working exclusively on the latter since 10 years on the characterization of resources and their exploitation, as well as on the risk and potential impacts related to geothermal installations. Okay, thank you, Pierre. It's all yours.
Thank you, Fernando. I'm going to share my presentation. Okay, is it okay for everybody?
Yes, we can see it.
Okay. Thank you. So I will talk a bit about the status of geothermal exploitation in France, but I will focus a little more on our system of permitting and data sharing, which is still pretty unique, I think. And okay, so for the status, if we are talking about conventional geothermal power generation in France, well, we have no current resource on mainland. It's not volcanic at the moment, and I hope it's not going to be soon. But we still have some resources overseas. So first in the Caribs, in Guadeloupe, where we have a power plant installed, but we have also a project in Martinique, still in the Caribbean, and in Mayotte and La Réunion in Indian Ocean. Our only conventional power plant for now is Bouillante in Guadeloupe, and it's only 15 megawatts of electricity installed. But there is current work and forecast developments to enhance it up to 50 megawatts. We also have some quite advanced project for electricity and cold in Martinique. I will not tell you anything about the cold because I'm not really familiar with the technique, with the technology. We also have in La Réunion, not La Réunion. Usually it's non-French people who make this mistake, but we have some less advanced project, but still, and also resource assessment in Mayotte. So we hope to develop power generation in our overseas territory, everywhere in when we have where we have volcanic context. Mainland, we have some enhanced geothermal system. Actually, it's only in the northeast of France, in Alsace, in Soultz-sous-Forêt, when we have our first EGS power plant installed. It's 5 kilometers deep, 170 degrees, and it produces, the installed capacity is 1.7 megawatts. And near to Souls, there is another installation running, but it's an industrial installation, not for electricity. It's 27 megawatts of steam used for agri-food. It's used for drying amidon. Currently, there are only 2 running in France, but there is some projects. In fact, we have actually 11 permits running in mainland in France and 3 overseas. Anyway, if everything is developed optimally, it's going to a power capacity of 166 megawatts. The currently installed electricity capacity in France is 130 gigawatts. So it's probably not going to play a big role in electricity production mainland. And for the future development mainland, well, it's principally a cogeneration of heat and electricity, because if you use it only for electricity, as we are doing in Souls, it's a bit costly. So you have to valorize it by also selling heat. But we are also looking about lithium extraction, because those the fluids are really rich in lithium. Actually, mainland, it is a bit slowed due to induced seismicity. We had some noticed seism due to one installation, and so French authorities and public are a bit cold about it now, but we are working on doing it, on going over it. As for direct use, in fact, it's quite developed in France. For example, in the Paris area, more than 400,000 people are heated by geothermal district heating. It's one of the more important concentration of geothermal district heating in the world, if not the most important. And it's with wells at around 2 kilometers deep and fluids around 70 degrees. But we have also district heating in other area in France, essentially in the geological basins. And if we are looking at the development, it is developing since 8 years now, with plans of still developing, because we still have a good potential. Currently we are researching and do exploration of new resources, and also there will be the installation of a new district heating network working with fluid with lower temperatures, so we will be able to valorize more resources. So there's good development planning for direct use. For shallow geothermal energy, well, after some really good start in the between 2005 and 2010, it's more slow now, and especially if you are looking for the actual production, the biggest production is for individuals, but it's the development, the current development for individuals is really slow, and it starts raising a little more for collective and tertiary. So collective and tertiary is principally offices, but also collective building, hospital and long-term care houses. And as I said, the development is not actually, but currently higher for the collective and tertiary. But we see more need, especially for cooling and refreshment, and also development of new sectors. I say new because it's not really new, but it was not well developed before, like agricultural, industrial, winemaking. We are in France. So there is still a lot of work to do on the development of shallow geothermal energy in France. And on a side note, we have a shallow geothermal testing platform at BRGM with multiple underground exchangers installed and fully monitored. So it's open to anybody that want to test some concept or some exchangers. But I'm going to switch to the main part of my presentation. First, if we are speaking about the mining code and the regulatory, well, first question is, does it have to be harsh? Well, yes, because in France it's ruled by the mining code and it is subject to authorization. It requires impact study and public consultation, and it takes more or less 1 year, and sometimes more, sometimes more, and sometimes really more, but not always. Because for shallow geothermal energy, as long as you drill less than 200 meters depth, and the installed capacity is under 500 kilowatt, and you are not in red zone, I will talk about this later, then it is a simple online declaration. So for the shallow geothermal energy, also known as geothermie de minime importance, which translates to not really that it's not important, but it has low inspected impacts, and from the administration, we don't have time to deal with that. So there is a decree that defines the terms of shallow geothermal energy backed by four orders. One is on general requirement, conditions relating to layout and installation, measure of the performance, conditions of size and exploitation, as well as surveillance and maintenance of the installation. And basically, it's a minimum requirement for installing shallow geothermal. We have also an order about qualification of drilling company. If you want to work on shallow geothermal energy, the drilling has to be performed by qualified companies. If the company is not qualified, they cannot work on geothermal installations. We have another on the cartography of statutory zones and also on the expert approval. I will talk about this. So what is the statutory zones map? Well, it's a map where we are doing a cartography of some of area level for some phenomena like contact between different aquifers, polluted zones, some particular geological setting like the presence of evaporite rocks or karsts or things like this. So all those areas are projected on a grid, 500 by 500 meters, but it can be refined. Then we are the area level is multiplied by aggravating factor and sum. There is difference between closed and open loop because the drilling technology is not the same. And then we arrive to a classification by a threshold, and we have 3 zones. Green zone, it's where it is a simple online declaration. You don't need any authorization. Orange zone, it's still an online declaration, but you need a certificate of compatibility from an expert. Basically, I don't think experts at now we have few. If we have experts that said no, but some said yes, but you have to use this technology for drilling or have special attention to this potential problem. And in red zone, you are going back to authorization problem. You still can do geothermal. You can still have geothermal installation, but you need an authorization. Okay, so we started with national maps for the whole depth range to 200 meters, and we are currently revising it on a regional scale with 3 depth ranges up to 50 meters, 100 meters, and 200 meters. Because if you have some potential problem at 150 meters, you still can drill down to 100 meters. And it's supposed to be, mainland is supposed to be covered by the end of 2023. And those statutory zones can be viewed online. We have a website for this. So you have the maps with the 3 colors, but also you can also have the reason why why your zone is orange or red. So you have the different criteria, and you can also look at the different criteria even in green zone to see if you have to have particular attention for some potential problems even in green zones. What is a bit special in France compared to some country is we have a national data collection. Every well of more than 10 meter depth drilled in France have to be declared. And you have to provide basic information like like location, depth, use, driller log, but you can provide also more information like pumping test, chemical analysis, thermal response tests, and data are collected in a data bank, and this database is public, minus some owner's personal info. And all the Geothermal online declaration are automatically versed in this database. And in fact, this declaration system is currently being extended to water and geotechnical wells also. And those data can be consulted also online by public when you have all the wells with different type of information depend of the well. So sometimes you have technical logs, stratigraphic logs, thermal response test, pumping test. It's not homogeneous, but we still have a lot of information. And from all this information, we can use it to create, for example, some 3D geological model in the Paris. It is in the Paris Basin. And for example, it was used to create a deep resources atlas here for the main aquifer used in Paris area, the Dogger. We have maps of aquifer depths, temperature, and transmissivity. And this is available online. And we are also doing a lot of use for resource assessment for shallow geothermal energy. For example, we have in some regions atlas of aquifer geothermal resource, and the information it's not really homogeneous. The informations range from the basic location of potentially useful aquifers to a fuel resource qualification from a 3D hydrogeological model. And we hope to one day improve it by shifting from productivity data to injectivity data. If you are not doing a lot of shallow geothermal energy in your country, the biggest limitation is more injectivity than productivity of the aquifer. We are doing the same from closed loop. Well, the most basic are based only on geological map, but more advanced are based on the stratigraphy along all the considered depths. And the next step will be to fit the theoretical conductivity to thermal response test data. So we are collecting and analyzing thermal response test at the moment. And all this is still available online for everybody. We had also made in some urban areas atlas of geothermal potential, combining resources, needs, and constraints. Here is an example around Paris with the energies that that can be provided by geothermal energy for heating in each municipality. And this, I think, is the beginning of real planification and management tools. Planification and management tools are useful for promoting geothermal energy, but also for avoiding potential problems. Like, for example, in Lion City area, we have an imbalanced exploitation that caused the temperature rise in the shallowest aquifer. Basically, sometimes they install a lot of cooling system on this shallow aquifer and still using natural gas for heating. So they are injecting a lot of heat in the aquifer and causing the temperature to rise, sometimes more than 5 degrees. So this goes to the creation of an observatory combining data collect, monitoring network, but also modeling with a thermohydraulic model. And in this case, it's something I think we have to learn to do a little more in the urban area. It's to model the flow, but around the underground structure, because the temperature rise is especially high when you have some accumulation due to underground structures. And well, but to finish and on the prospects on geothermal energy in France, as for power generation, overseas we have a good potential development, and it may become one of the primary electricity source in insular context, really. But mainland, we can see that, well, first, that future projects should be coupled with heat production and or lithium extraction, because economically it's a bit difficult if you are doing only power generation. And it's still not bound to play the major role in the French electricity mix. For direct use, it's a bit different. It's something that is actually important and has a good potential to growth with the exploration of new resources. And we have also a very large potential for new low temperature district heating networks. For shallow geothermal energy, well, we are currently doing an active promotion of the development with communication, regulatory, funding, resource assessment. We are also working on exploitation optimization. And one of the big actual things is the integration with other energy sources. You can use a shallow geothermal as a baseline with with intermittent energy sources. You can also use it to store heat or cold. So we are probably mainland. We are trying at least to develop the direct use and shallow geothermal use. As I said, for the power generation, there is still interest, but it's not going to be the thing for electricity mainland, but it may become one of the big things in overseas. So, thank you for your attention.
Thank you so much, Pierre. It was a very interesting topic, and thank you for the information. Now, we have a question from Daniela. Pierre, the Sul-sur-Forêt power plant is currently still operating and generating electricity for the national network. And are there any issues about induced seismicity?
No, there was one little event during a stimulation phase, but it doesn't do any damage. and it's not in a very populated area, so no. But we had some problem in east of France, in Strasbourg.
Okay, and the power plant is still operating, right? And
Yes.
generating electricity. Okay.
Yes.
Okay, thank you. Now, moving on with the presentations, we have Christophe Kerbevan. Christophe joined BRGM in 1992, where he worked essentially on the development of the first in-house coupled reactive transport numerical models that were initially used for various environmental risk management applications. From 1993 to 2012, he has been notably involved in several national and European projects on the geological storage of CO2, where he has contributed, managed, or led the modeling tasks on water, gas, rock interactions. Christophe is going to talk about CO2 dissolved, how geothermal doublets can help reduce industry's carbon footprint. Thank you, Christophe, for being here today.
Thank you for the invitation and for the opportunity for giving this talk. Yeah, so first task, I have to share my screen. Hopefully it's going to work. Is it okay?
Yes, we can see it.
Okay. Then, oh yes, the sound is. So yes, my talk today will be about specific use of geothermal doublets. So we are here talking about geothermal, direct use of geothermal energy type of facilities. And I'm going to present the CO2 dissolve concept we've been working on for now more than 10 years at BRGM. And I'm going to show you how geothermal doublets can help reduce industry's carbon footprint. So first of all, I'm going to present the CO2 dissolved concept. So as I'm totally unable to present it in less than 10 or 15 minutes usually, so we've made a video which is 2 minutes only, and you should be aware of the whole system in just 2 minutes. So just tell me if you can't hear the sound. I have a plan B in case it doesn't work, but we did some tests and it works.
CO2 Dissolved is an innovative CO2 capture and storage concept developed by BRGM and its partners since 2012. Particularly well adapted to industries with low CO2 emissions, CO2 Dissolved offers a solution to eliminate or significantly reduce their carbon footprint. The technology consists in storing CO2 fully dissolved in the water of an aquifer, deep down in the subsurface. This water is far too salty to be used as drinking water, and it has the advantage of being naturally hot, with temperatures between 40 and 90 degrees centigrade. The hot water is first pumped up through a well from the aquifer to the surface in order to recover the energy, which can be used, for example, to supply a heating network for homes. Once the calories have been removed, the cooled water is then used to dissolve the CO2, previously captured from the factory fumes. The cold water and dissolved CO2 are then re-injected into the same aquifer via a second well. This pumping re-injection cycle using a set of 2 wells, called a doublet, operates continuously, as in any classic deep geothermal installation, a technique widely used in the Île-de-France region in the Paris Basin. The difference here is the addition of CO2 in dissolved form in the re-injected water, with a maximum concentration of around 50 kilograms of CO2 per cubic meter of water. Calculations show that it would be possible to store in this manner up to 80 to 150,000 tons of CO2 per year per site, In France, more than 400 industrial sites emitting low quantities of CO2 have been identified that also have underground geothermal resources. This combination enables the potential implementation of CO2 dissolved. Should CO2 dissolved be deployed at all compatible sites, this would remove the equivalent of the annual CO2 emissions of 12 million cars. CO2 dissolved therefore offers a win-win environmental and economic benefit by reducing industrial CO2 emissions while producing clean and renewable energy. This technology brings an innovative solution to small industrial emitters scattered across the territory, allowing them to reduce their carbon footprint and thus contributing to the major challenge of climate change mitigation.
Okay, so as a reminder of what was presented in this video, you just have to keep in mind that in this CO2 dissolved concept, which on some points has some similarities with, if some of you were attending the previous presentation of the COP/FIX option that is used in Iceland, there are some sort of common features between those two, but some differences as well. So the CO2 is stored in a deep aquifer as being entirely dissolved in brine, and this is something important. If you are familiar with carbon capture and storage (CCS), then the option generally used so far is storing CO2 as being a supercritical phase in either aquifers or depleted oil and gas reservoirs. So here it's something different, as we want to keep CO2 entirely dissolved in brine. So this is the first point. The second important thing is that as an additional beneficial operation in storing CO2, you have geothermal heat production. So or if you consider that geothermal heat production is the primary objective, you can have some additional benefit in storing CO2 over nearby industrial emitters. So you can look at it both ends. But this is very important and makes a difference with standard CCS, where you don't have this additional benefit because you don't produce geothermal heat generally. Also important is the fact that it's a local solution, which means that both CO2 capture and storage and heat production are operated on the same industrial site. So we get rid of the transport part of the CCS, which is not the most expensive part, but it's somewhat the more difficult to implement, because you have to install some kilometers or hundreds of kilometers sometimes of pipelines, or use trucks or boats or trains or whatever to transport CO2 from the emission site to the storage site. Here, everything is on the same site, which simplifies things. And another important thing and feature of this CO2 dissolved approach is that it is safer than standard CCS, because we avoid the presence of a big gas bubble in the underground, which because of the density effects has a tendency to goes up in the reservoir, and we can have some leakage of CO2 if the cap rock of the reservoir is not perfectly sealed. So here in this case, we don't have this issue. So this makes it much safer, much lighter in terms of infrastructure, as I told you before. And of course, as it is lighter, it's certainly less expensive than a big hub of standard CCS. But the constraint is that because of the limit of solubility of CO2 in water, or in geothermal brine, in this case, this approach is really devoted to small industrial emitters, which could be scattered over a large territory. If they are scattered, this prevents us from thinking about building a big hub of CO2 capture and then send all the CO2 to storage sites. So it makes no sense from an economic point of view, and probably on an environmental point of view as well. So here we plan to apply this technology specifically to small territories with small industrial emitters. But yes, sometimes small is beautiful. So okay, so now if we have a quick look at the typology of the industrial CO2 emitters in France. So as the topic today is France, yes, I've also focused my presentation on France, as you will see. But this emitter, so of course France, because we have a lot of nuclear power plants, I would say that the landscape is a bit different than what we can have in other European neighbors, just like Germany, for instance, where much more natural gas and coal are used to produce electricity, for instance, even before the war with Ukraine, between Ukraine and Russia. So in France, we have typical power plants, metals, minerals, waste, petroleum and natural gas, chemicals, pulp and paper, and some others. And as you can see, the blue bars are referring to a total amount of CO2 emission in million tons per year of all the emitters of a certain type, of certain category. And in green, the green bar represent what is emitted from small to medium CO2 emitters. And typically they are emitting between 10 and 150 kilotons per year. So as you can see, of course, the majority of the emissions come from the big emitters, but the small emitters do not count for nothing, at least in France. And if we now on the right graph look at the number of emitters, this was a surprise for us at the very beginning of the project, that we have a majority of small emitters in France. It's about 80% or maybe more than 80% of the industrial CO2 emitters are small emitters. A certain amount, 160, are average emitter between 150 and 1 megaton of CO2 per year, and the big one are not. So there are not so much big ones, a 10, so yes, 20. Oh, this number is our 2011 numbers. They are a bit old. I need to update my slide one day, but I think the general orders of magnitude are still good. And now, if we look at the graph at the very right of the slide, you can see that, of course, and with no surprise, this CO2 emissions coming from the small emitters are accounting for about 25% of the global emissions. So, but we have to keep in mind that the average emission rate of all French emitters, big, small, and medium, is less than 150 kilotons per year, which means that in average, most of the CO2 emitters, industrial CO2 emitters in France, are potentially compatible with the CO2 dissolved, at least in terms of amount of CO2 emitted. And now, if we focus on the what is the main target for CO2 dissolved, the small industrial emitters, the average is pretty low. It's less than 40 kilotons of CO2 per year, which means that we should find a lot of them compatible with CO2 dissolved, provided that they are located in places where we have some geothermal potential. So now, if we look at this geothermal potential, and if we have represented on this map, in blue are the main areas recognized as potentially providing geothermal potential, and all the colored dots represent small emitters with category of emission depending on the color. But as you can see, a lot of them are located in the blue areas, which means that they could be potentially compatible with the CO2 dissolved approach. Actually, it is more than 400 of them which are compatible, and they all emit altogether 17 million tons of CO2 per year, which means it's far from being negligible. And they represent 12% of French industrial emissions. Only the sites on the blue areas on the map. And now, if we focus on the two main sedimentary basins in France where geothermal energy is exploited, it's more than 300 of them, which could be compatible. All of them emitting almost 13 million tons of CO2 per year. So if we extrapolate all that, and being somewhat optimistic on the future of the development of CO2 dissolved, if we deploy if we would deploy this technology only on 25% of the sites represented on this map, and which are in these two basins, so 25% of these 330 sites, we would meet with just capturing the CO2 emitted, we would meet 20% of the SNBC objective in 2050. So SNBC is the French national low carbon strategy. So it has been defined by the government for the next year until 2050. And what is in the plans of this SNBC is capturing by CCS technology 15 million tons of CO2 per year in 2050. So just with CO2 dissolved, we could provide 20% of this objective. Also, in terms of economics of all this, we can calculate, assuming a 100 euro per ton for the CO2 price. Currently in the market, I think we are about 80 euro a ton. So 100 is not that far. We could generate a potential CO2 market of 300 million euro per year, which is also something significant. And that starts to be interesting for more and more industrial companies. And at the same time, we could produce 3,000 gigawatt hour per year of geothermal heat, which is also something significant. It's I think it's about, from the numbers I've found in the literature, is about twice the current value of the heating networks, district heating networks, the energy, geothermal energy used in those networks. So it's something really significant. So now an important thing, because we are initially we were talking about CCS, a CCS option, of course, closely related to geothermal heat production, but mostly the important thing is to try to assess what could be the performance of such a system, provided that so far we didn't find any major reason to have a negative impact on the geothermal heat production, adding some CO2 in water. So so we are focusing on the CO2 storage performance. And from 3D modeling, we have performed a lot of simulations, and one of the main feature that has to be considered when talking about CO2 dissolve is illustrated on that figure, is the fact that when you're injecting CO2 on an injection well, inevitably after a certain time you will produce some CO2 at the production well, which doesn't mean at all that this CO2 is going to go back to the atmosphere. Otherwise, all of this would be of no interest. But at least it is included in the geothermal loop at surface, and has to be managed so that when adding some more CO2 from the amount of CO2 you're capturing from the industrial site, you have to remain always under the limit of approximately 50 kilograms of CO2 per cubic meter to remain entirely dissolved. So this means that because of this inevitable phenomenon, which is actually something similar that what you observe in I would say standard geothermal doublet, where after a certain time you are cooling your resource, and then you are producing lower temperature water, so which makes it less interesting in terms of economics. So here we have the same problem, the same issue, but it's a much faster phenomenon because it's mass transfer to be compared to heat transfer, which is much slower. So here, if we look now at the what CO2 injection rate curve could look like, here we are in kind of a worst case, in the sense that we are assuming injection of the maximum concentration of CO2 at the very beginning of the operation. So this, which means from T0, we are injecting at a concentration of about 50 kilograms of CO2 per cubic meter of water. So which means that we are at the limit of the CO2 solubility in brine. And then what you can see, so all this curve, what varies with this curve is the flow rate of the geothermal doublet from 100 to 300 cubic meters per hour. So of course, if you have a high flow rate, water flow rate, you will have at all the concentration being equal in 3 cases, you will have a higher injection rate, but more quickly, this injection rate is going to decrease due to the fact that you cannot add more CO2 to the water because you are producing some of the CO2 you have previously injected in the production rate. So one important parameter is the flow rate, of course, the water flow rate, the CO2 concentration in the brine, and also the distance between the wells in the reservoir, which is typically on the order of 1 kilometer, generally, at least what we have in the Paris Basin, and sometimes more, between, let's say, between 1 and 2 kilometers distance between the wells. And here it's some sort of average test case. And what you can see is that, of course, the more you increase the flow rate, the shorter is the time during which you can inject at the maximum flow rate. So you have to take this into account. And this is something that has to be managed and surfaced by measuring and monitoring the concentration in CO2 at the production well. But now, if we calculate the cumulative mass of stored CO2 over a period of 30 years, well, we have chosen 30 years because it is the typical lifetime of geothermal doublets. So that's why we have considered this lifetimes for the system. But as you've seen in the previous slide, the system can work beyond 30 years. You are still storing some CO2, but you're storing less, but you're still storing CO2. But if we calculate basically the integral of the curve previously shown, we can see that, of course, the higher the flow rate is, the higher is the amount of CO2 that is stored, definitively stored in the reservoir. And of course, as you increase the distance between the wells in the reservoirs, you increase the amount of CO2 because you maximize, or you maximize the transfer time between the injection and the production wells. So this curves are not a surprise, but they give you some orders of magnitude of the amount that could be stored with this system after 30 years of continuous injection, it can reach in almost all the cases and go beyond 1 million tons of CO2. And but this, as I told you, this example was kind of a worst case. And now, if we go back to more representative values of the CO2 emissions of the industrial emitters in France, which are on the order of 38 kilotons of CO2 per year. If you have, let's say, an average, this is an average performance geothermal doublet, 200 cubic meters per hour, and an average distance between the wells. You can see on the blue curve that rather than starting from the beginning from 100% saturated water with CO2, you only need to saturate 50% at a 50% rate to reach the 38 kiloton per year, which is the average typical of French industrial CO2 emitters. And then with this value, you can inject almost during 30 years at a constant rate, and the decrease is pretty slow at the end. So, which means that this is like this type of curves are likely to be representative or more representative of what could be the average an average system, at least in France. And if you need less CO2 to store, just like 25 or 20 on the red and green curves, you can see that you can inject with no problem during 30 years and probably a few tens of years after that at a constant rate. So this is really interesting. Okay, so now just to tell you where we are in the development of this concept. So this is the history line of this concept. We started from a first project called CO2 Dissolved in 2012, and then this project lasted 40 months, and the aim was basically to work on the technical economic pre-feasibility studies for this concept and see if it could work. So we mostly work on the technical part than the economic part, but all the results were positive, so that we were able to have another project funded by another French funding system, Geothermal, where we had this pilot CO2 dissolved project, quite a short project, in which we worked on well, we initially aimed at finding a demonstration site, but it was a bit early, and then we do some pre-feasibility calculation at the very end of this project on the real site, and the results were positive, but the industrial company did not want to go any further, so we stopped there, but the results were positive. And we started also some complementary studies on, of course, on the scientific aspects, but also on this regulation. As Pierre mentioned earlier, the regulation in France is a bit complex, and here we add another part of the regulation devoted to CCS, which makes it even more complex than standard geothermal doublets. So it's really something we have to work on, and also in terms of sociology and public acceptance, this is something we have started to work on in this project. And another important thing we've done in this project, but I really don't have time to show you more about that, is that we've been working on a CO2 capture technology. It's something new and relatively different than what can be found on the market, because it's a system where the solvent used for capturing CO2 is water, and actually we are with this system we are also dissolving CO2 in water. That's why it's very much synergetic with the CO2 dissolved approach, because we are relying on the same basic process. But maybe I can say a word if there are any questions about that, but I don't have time to present things about that. And then we had another project, CO2 dissolved injection, where the idea was to definitively validate the technical feasibility of injecting CO2 as being entirely dissolved in an old geothermal doublet. Of course, using an old geothermal doublet prevented us from drilling a new one. So in terms of cost, it was much less expensive. And so actually this project is still pending, because we've got funding for the first part of the project, which aimed at finding an appropriate site, which was not very easy actually, because we need to have agreement of the owner of the site to so that we can play on his site. And well, we have identified one, and we have prepared all the technical plans. We have calculated the budget and the main task for doing the job, but we are now lacking funding for during the operation, the actual operation. So, but hopefully we can find a way to get some funding to perform this test. Let's say sometimes in the second half of this way, or next year, more likely. And we had also another project funded by the Centre Val de Loire region, which is actually south of the Paris Basin area, and which is the region where I'm talking to you right now. We are BRGM main offices are located in Orléans, which is one of the big towns in this region. And the region funded this project because they were interested by the CO2 dissolve approach. And what we proposed to do was to do a more detailed inventory of the potential sites that could be compatible with the technology in this region. And the main outcome of all this is that there are a lot of potential sites compatible in the, well, a lot. I mean, at least 10 or 15 of them among only 40 industrial sites emitting CO2 in this region, which is not a very big industrial region. And we are now in advanced contacts with at least 2 industrial companies which interested in this technology. And of course, as you can guess, most of the work is to do some financial engineering work. Yes, we need to find money to do those tests because it's a bit expensive, but not that much expensive. So we are pretty much confident on the positive outcome of this project, so that we can sometimes after 2022 probably be able to set up the first CO2 dissolve demonstration pilot on an industrial site. So we already have at least 2 industrial sites in the Centre Val de Loire region. We can find others. We are also discussing in other parts of France with some other industrialists. So it's really active at the moment, and we hopefully be able to present in a couple of years some more information about this pilot somewhere in France. So, and to conclude this, what you have to keep in mind is that this CO2 dissolve concept is based on an existing technology. The core of the system is the low enthalpy geothermal doublet, which means that this technology is mature and is generally well accepted by society because of no induced seismicity in this kind of exploitation. And so this should facilitate the development of the CO2 dissolve technology, according to us. And as I told you, also the fact that CO2 is entirely dissolved in water offers many advantages, and mostly in terms of safety and hopefully in terms of social acceptance. But keep in mind that there are limitations, well, physical limitation in terms of CO2 solubility in brine, which led us to focus on small industrial emitters as being the main target for applying this technology. And of course, you will probably all agree with that statement that we need a pilot to validate the full concept and assess the actual CO2 storage performance, and also confirm that it has a low impact or maybe no impact on geothermal heat production. So, as I told you, we are currently working hard on this, and we expect to have some positive outcomes in the coming months. So CO2 dissolve really is an interesting option to consider as a contributive solution to climate and energy crisis. It's suitable for reducing the carbon footprint of those small industrial emitters, and And we have a lot of small industrial emitters. And most of them have no solution because some emissions are not due to the energy they use, but it could be the result of the process itself. So they can't reduce that. And it certainly is a complementary solution to classical CCS, which is more devoted to large amounts of CO2. And of course, there is this important and additional benefit with production of renewable energy. So this makes the CCS approach really, really different. And we are convinced that CO2 dissolved can help fostering geothermal energy use. Of course, in compatible territories, but where you have scattered small industrial emitters, just like in the Centre-Val-de-Loire region. And also in territories with large geothermal potential, which is still underexploited. So we have, as Pierre mentioned, also we still have some potential to use more geothermal energy in the coming years. And of course, this could be interesting as well, close to densely populated areas with heating and cooling needs, even though you can consider that in some cases, the geothermal heat produced can be directly used by the industrial emitter for its own needs. So we can also think about using geothermal energy for other purposes, just like, for instance, heating nearby greenhouses, which is an interesting application. We previously had some discussion with Dutch colleagues, and of course in the Netherlands we have a lot of greenhouses, and they are already, some of them are already heated by geothermal energy. So this could be an interesting application. So I think that's all I had to tell you today. So thank you for attention, and I'm of course open to any question you may have.
Thank you so much, Christophe. Really interesting presentation. Pretty informative. I have a question here from Daniela. She says, really interesting your talk. Thank you. What modeling software have you used for the simulations you showed?
Yeah, actually we use an in-house hydro geochemical modeling code, which is named MART. And this code can be coupled with Frixie, which is a well-known geochemical modeling tool. So, so what I presented today was non-reactive transport modeling, but we also had performed some reactive transport modeling, so coupling MART with Frixie.
Okay, thank you, Christophe. And thank you and Pierre for your presentations and your time. Do you think you can send us these presentations to upload them in the platform, just to have the presentations in the Geotheroom platform?
Okay, no problem, I can do that. But probably I'm going to remove the video and put a link to the YouTube page, because it's a bit heavy otherwise.
Yeah, no problem.
Okay,
we can have the link placed on the platform.
Okay, no problem.
Thank you, Christophe. And thank you, Pierre. And that will be it for today. Thank you so much for your time, and to the assistants. Thank you for being here. Christelle also, she's a collaborator on behalf of France. And see you then on July 22nd for the Sweden's presentation.
There is one more question on the, but it was sent only to me. So.
Yes.
But it's for Christophe.
Yeah.
Did you take into account the corrosion of the casing during the injection?
Yes, this is an issue we have identified very early in the very first project of the series, the CO2 dissolved series, and we've been working with a BRGM subsidiary named CFG, and they are a specialist of operational geothermal energy production. So we've been working with them, and they, of course, the corrosion of the steel casing is an issue generally, but this is enhanced by the fact that we inject acidified water dissolving CO2 in it. And the solution, the best solution found was to use reinforced fiberglass for the well casing rather than steel. And this is something we have well, at least CFG has good experience with this type of material, and they are now very reliable for geothermal wells, and they have the advantage to be insensitive to corrosion, which makes a big difference in this kind of applications. And even on standard geothermal, I would say it's interesting to use this type of material, even though it's a little bit expensive, but you have less. You don't have to use corrosion inhibitors, for instance, with this type of well. So this is interesting.
Thank you, Christophe. So, so that will be the end of these presentations.
Okay.
Right? So thank you so much to you, Pierre, Christophe, and Christelle as well, and our participants. See you on Sweden's presentation.
Okay.
Thank you.
Bye-bye.
Goodbye.
Thank you. Goodbye.
Bon weekend.
Thank you.
Yes, it's a long weekend for us. Yeah.
Profitez.